In this module, we look at how WFSTs are used to build a speech recognition system. So the generic algorithms that we studied for WFSTs in the previous couple of modules, we're going to concretely apply them to the ASR problem. Okay, so here is the kind of cascaded WFST based ASR system. So you start with what I'll call acoustic indices, and I'll qualify just in a moment. Think of them, these acoustic indices, as being indicators to HMM states. Okay, and I'll elaborate on that in a bit. So I have an acoustic model, okay, which is for now, which is HMM based. So it takes in a sequence of these acoustic indices and it needs to throw out a sequence of corresponding triphones. Okay, so that's the goal of the acoustic model. So now I can compose this WFST, which produces triphone sequences as outputs, with a machine which I'll call a context transducer, whose only job is to map a triphone sequence to its unique corresponding monophone sequence. So this is a deterministic machine. Given a triphone sequence, there is a fixed monophone sequence, underlying monophone sequence that it maps to. And the context transducer should implement that mapping for me. Okay, so now once I have these monophone sequences, what is the goal of the ASR system? Let's assume it needs to throw out word sequences, right? So I need to find the best word sequence corresponding to a speech signal. So I need to go somehow from monophones to words. And for that, I'll have a pronunciation model or a dictionary, which consists of mappings of phone sequences, monophone sequences to words. Okay. And finally, this is not telling me what are kind of acceptable sequences of words that can come together. And that's where the language model comes in. Now, the language model is a finite state acceptor. Okay. The only symbols on the arcs of the language model correspond to words. So it's an acceptor. And its only role is to reorder the probabilities of word sequences. Okay. So that we pick up word sequences which are much more likely in a particular language. So if I compose this sequence of 4 machines, which we will designate with very specific symbols, and these same symbols are used in the Kaldi toolkit as well. So it will be of use, and also in the reference PDF, which I'll be sharing on Moodle. Okay, so now let's step through each of these individual components in more detail. So the very first machine is what we're going to refer to as H moving forward. So H is this acoustic model HMM based FST. How do we build this FST? Okay, I have one 3-state HMM for each triphone, right? We know this from going through HMMs for building the acoustic models. So here, first off, the H is a weighted FST. So here there are weights accompanying each of these arcs. And these weights are just the transition probabilities from your HMM. Okay. How we bring in the observation probabilities of the HMM, that's going to come up in a few slides when we talk about the entire decoding procedure. But for now, it will suffice to know that the weights on H correspond to the transition probabilities of your HMM. Okay. So here are your 3-state HMMs for each triphone. Now, what are the input and output symbols on each of these machines? The input symbols are these indices here, which I'm denoting by some F0, F1, F3, F4, F5, and so on. And each F sub I, it maps to a distinct triphone HMM state. Okay, so think of these indices as being indices for the various states across all the triphone HMMs. So if I want to refer to this particular state, which is inside this particular triphone, right? So here, I mean, this is the middle phone, this is the left context, and this is the right context. So if I want to refer to this particular state, so that's the 3rd state in the triphone corresponding to A plus B, then the corresponding index is F5. Okay, so that's all. So that's what these acoustic indices mean. They are directly giving me an index into a specific HMM state inside a triphone. All right. And what appears on the output side? So let's move forward. So how do I build this entire HFST? I have each of these individual three-state HMMs, one per triphone. I'll take the union. So I have a new start state. I'm going to take the union of all of these FSTs corresponding to each triphone HMM. And I'm also going to apply closure so that I can deal with sequences of triphones. Okay, so there is also closure. So from each final state, I'm going to return back to the start state. Okay, so how do I kind of define the output labels? So from here, I'll have an epsilon transition to the first HMM. At the very first transition, say that I produce the corresponding triphone as my output label. And then subsequently, all my output symbols are just going to be epsilon, as long as I'm within that particular triphone. Then the minute I exit this triphone and I enter, say, some other triphone, then in the very first arc, I'm going to spit out the corresponding triphone label. And then as long as I'm within that triphone, it's going to be all epsilon output symbols and so on, right? So that's the kind of manner in which this particular FST behaves. And so here, here's one small subtle thing. I'm going to start with a sequence of acoustic indices, okay, which will be the same as the number of speech frames in my utterance, in my speech signal. So that's the granularity at which the input symbol sequence appears. But because of all these epsilon output symbols within each HMM, what is the resulting output sequence? It's going to be just a single triphone sequence. Okay, so the number of output time steps, if you will, in the triphone sequence will be considerably smaller than the number of input time steps, which corresponds to the speech frames, right? And this is again the kind of power of WFST, that it allows you to reason at different granularities just with the help of these epsilon symbols, epsilon transitions. Okay, so that's my HFST. So just the main points again. The input sequence is a sequence of acoustic indices where each of these indices map to a distinct triphone HMM state, okay, within my set of all triphones. These could be tight state triphones or untight triphones, whatever it is, right? And the output sequence is going to be a triphone sequence. Okay, so now that's the output of H, and the weights of H are going to be the transition probabilities. Now, what do I do with these triphone sequences? So I want a deterministic machine, which I'm going to refer to as C, which takes a triphone sequence. So say I have hello world, right? The corresponding monophone sequence would be hello world. So this is the monophone sequence. And this has a distinct triphone sequence. So I'm going to switch notation and use this notation which is in this paper, because this is going to be a required reading. So the notation they adopt here is that you have a monophone. Don't look at the monophone on the left side of the colon, but only look at the triphone notation. Okay, so they have phone followed by left context underscore right context. So that's going to be the very first triphone here, right? So this is followed by phone in the middle, the left context underscore the right context, and so on, right? So given such a triphone sequence, I can uniquely map it down to its corresponding monophone sequence. And that is exactly what this machine C is going to enable. That it's going to take a valid triphone sequence and map it down to its corresponding monophone sequence. And here is what that machine would look like. Okay, so this is one version of C inverse. Okay, so this actually, remember the notation on each transition, you'll have an input symbol colon output symbol, right? That's the notation on each of your transitions. So here the input symbols are monophones, and your output symbols are entire triphones. So here they've actually built C inverse, okay, which takes a monophone sequence and produces the corresponding triphone sequence. And since this is deterministic, you can take the inverse of this machine once it's constructed, and then you have C, which will take you from triphones to monophone sequences. Okay, so if you're wondering, okay, this machine looks a bit scary, how, say that, I needed to build such a machine, how would I go about it? Okay, so let me just give you a sketch of how this, you could imagine building such a machine. It's not very difficult. So let's say this is your start state. Okay, so what I'm saying is, okay, first let's transition from the start state. So remember, I'm building a machine which looks like C inverse. Okay, so it's going to take a monophone sequence and is going to produce a corresponding triphone sequence. So say that I see some monophone A. I don't produce anything. Okay, I'm going to produce epsilon as the output. And I come to a state now which remembers that I consumed A. Okay. Now, just as shorthand, I'm going to say, let's assume that I'm going to have one such arc for every monophone symbol. Okay, so you need one such arc from for every monophone symbol from your start state to various states which remember the corresponding monophone symbol. Now, from here, I'm going to make another transition. Okay, now assume here that the monophone that I'm going to consume is B, which means now A is my middle phone, and this is the corresponding triphone, which I should produce as my output. Why? Because, so look at these two, the sequence of these two transitions. I consumed A, the monophone, and then I consumed B. Okay, so what is the underlying triphone that I am dealing with? A is the middle phone, my left context is empty, and my right context is B. Right, so that's exactly the triphone that I need to produce as output. So now I've transitioned into another state. Now let's say that, okay, this is AB, right? So I know that I've seen the sequence AB. So this, I need to construct such equivalent states for every AB pair. Okay, so you'll have transitions out from A to every other kind of AX, AC, all the possible triphones, and then for all A's, so for all A as well, right? So imagine constructing such arcs for every AB in your monophone vocabulary. Okay, so now once you have AB, you can have transitions out of AB to other consistent states. So by consistent states, I mean, so if I'm at state AB, then I can certainly transition to a state which remembers BC, right? So then the monophone I need to consume is C. And now what does the triphone look like? The middle phone is B, my left context is A, and my right context is C. So ABC is the triphone I need to spit out, right? So this is a legitimate transition going from AB to BC, but I can't go from AB to XY, right? Because there is no continuity in that particular triphone. So imagine adding such arcs. So all these kind of consistent arcs. Okay, so do that. So for every AB, make sure there is a transition to every legitimate BX. Okay, so now once you've done this, now there are just a couple of more arcs to consider. So one arc is, so say you're sitting at A, okay, and from here you're done. You're already going to, you're done with the sequence. Okay, so before I show you that arc, let me also add, let me start from the easier setting. So say I'm at state AB, okay, and now I'm done. I'm ready to end this particular sequence. So you'll have a transition to your final state. And here I don't consume anything because I'm done. Okay, and then the only triphone that is remaining to produce as output is that B is the middle phone, A is my left context, and epsilon is my right context. So from AB, on this transition, I can terminate and reach a final state. Now, what if I go a little earlier in my context, and I'm now considering this state, which is just remembering A, having seen A. Now from here, if I want to terminate, right, Then I'll have an arc which is going from here directly to my final state. And this again consumes nothing. Okay, and this, what does this mean? That A is my middle phone, and my left context and my right context are both epsilon. Okay, so I just saw the monophone A, I'm done. I want to terminate. Okay, so this arc enables that kind of termination. That's it. Now you add these kinds of arcs for every other A, every other AB, and you're done. You'll have a machine which looks very much like this machine. So instead of doing this inverse and then first constructing monophones or triphones and then inverting it, I think it's also easy to think about directly going from triphones to monophones. Okay, so here's one way in which I would think about building such a C machine directly, not kind of tackling C inverse and then inverting it. So here now on my input side I want triphones, right? So how about we directly go to a state which remembers, say, some BC, which means so I have a triphone where B is my middle phone, A is my left context, C is my right context, and I'm going to produce A as the monophone. Okay, so this is that is what this particular transition signifies. So similarly, I'll have states which are encoding AB, CA, BX, CX, and so on. Right? I'll have all these kinds of pairs. Now you need to add transitions which enable consistency, meaning I can go from BC to say CA. So if I'm going from BC to CA, what would be the corresponding triphone? C is the middle phone, left context B, right context A, and I want to produce B as my corresponding monophone. Okay, and similarly, you can go from BC to CX, right? So that would be, say, C is the middle phone, B is my left context, X is my right context, and I'm producing B again as my monophone. And you have all these kind of consistency arcs. And then from each of these BX, BC type states, I'll have one transition which is saying don't consume anything, produce B. Okay, so now I remember that I'm at C. And then again, do the same, which is you don't consume anything, produce C, and terminate. And I'll have these kinds of arcs, these two epsilon input symbol arcs from each of these states. This is directly C. Okay, instead of kind of thinking about C inverse and so on. So you can, whichever seems more intuitive to you, you can accordingly build the machine. Okay, so this is my context dependency transducer. Okay, what's next in the pipeline? It's the lexicon FST or the pronunciation model FST, which is denoted by capital L. Okay, and what is its objective? To take a monophone sequence and map it to a word sequence. So here, this is a dictionary FST, which, and this is with closure so that you can deal with word sequences. So here you will see a phone sequence. So say you see D, A, T, so data, and then you'll spit out the word data, and then after that it's all epsilons, right? Until you have completed that particular word, and then you return back to the start state and do this all over again. So now you're mapping a a phone sequence to a word sequence. So the dictionary FST, it's intuitive that you can apply the optimizations that we learned about in the previous module directly to a dictionary FST. So this is what kind of an unoptimized dictionary FST would look like. Okay, so here, and this is not deterministic, right? Because on the same input B, you're producing two different words, similarly for C and so on. Okay, so now you can imagine determinizing this and you'll end up with this kind of prefix tree trie-like structure, okay, which is now determinized. So you're guaranteed that you're not going to have two different transitions for the same input symbol at a particular state. And finally, this is not optimal in terms of the number of states in the final machines. You can further minimize this determinized dictionary FST and it will look something like this. So it kind of collapses suffixes as well, which are common. And so now you have this minimal machine in terms of the number of states and number of transitions. Okay, so you can work with these kind of minimized dictionary FSTs, except There's a small complication when you think about L composed with the language model FSA G. Okay, so I'll come to that in a couple of slides. Okay, so that was my dictionary FST, and the final machine in this pipeline is my language model finite state acceptor, okay, which we'll refer to as G. G for a grammar FST. Okay, and here's a very simple language model finite state acceptor. So I'm just saying here you can traverse a particular word sequence and it will be accompanied by a particular weight, right, for a path for a word sequence, which corresponds to a path in this machine, and that is the likelihood of this word sequence for this particular language according to your language model. So the next module, we're going to focus entirely on language models. We're going to introduce n-gram models, and I'll talk about in more detail how to represent an n-gram model as a finite state acceptor. Okay, so then you can just plug that into G, and that is exactly what you will be using in your assignment as well. Okay, so here's the entire pipeline. You have H, C, L, and G. Okay, if you compose all of these machines together, you'll end up with what we call a decoding graph denoted by D. And we don't just do a naive HCLG composition, but we're going to use the optimization algorithms that we have previously seen to make this a compact machine. Okay, because the decoding graph inherently is going to be very, very large. So it'll really help if we can, and also searching this. Eventually, you want to search through this graph, right, for the best word sequence corresponding to an input speech sequence, speech signal. So if it's deterministic, search becomes very, very efficient. So it's really beneficial to try and think of building minimal deterministic machines, okay, that you can search over. All right, so here is a optimization sequence that people have identified, which turns out to be most effective. So you start with composing L with G. Now you determinize this machine. Okay, left compose it with C, which is C is already deterministic on its own. But now the entire thing you can further determinize. Then again, left compose with H, further determinize, minimize, and that is your resulting machine, okay, which is the decoding graph D. Now think about L composed with G. Okay, is L composed with G determinizable by itself? So the answer is no. Okay, and why it's not determinizable is, so one easy way to think about why it's not determinizable is if you consider the case of homophones. So by homophones, we mean words which are distinct but have exactly the same pronunciation. Okay, so what are some examples of homophones? So say you have the word read versus the word, say, read. So these are two distinct words, but they have exactly the same pronunciation. Say you have new versus new. Exactly the same pronunciation, but two distinct words, and so on, right? So given a phone sequence, it can map to completely two different distinct words, two or more, right? So homophones immediately make L composed with G non-determinizable. So how do I resolve this? Okay, I need to introduce what we'll call disambiguation symbols, or in the reference paper you'll be reading, they also refer to these as auxiliary symbols. So these are just think of them as some bookkeeping symbols which are added to L such that L composed with G is going to become determinizable. Okay. So the idea of the disambiguation symbols is straightforward. How would I deal with, so first is monophones. I'll have the same pronunciation but mapping to different words. Another setting where disambiguation symbols are useful is when the pronunciation of one word is a prefix of the pronunciation of another word. So for example, say cat, okay, cat, and the word, say, caterpillar. Okay, so the pronunciation of cat is a prefix of the pronunciation of caterpillar, right? So there is this creates this problem of a delay on the output side. Okay, unless I see the complete input phoneme sequence, I don't know what the resulting word sequence could be. Okay, so this is also a source of ambiguity. So these disambiguation symbols also help in disambiguating between such pronunciations, okay, which happen to be prefixes of other words' pronunciations. So, what would you need to do? Just add a new symbol in the pronunciation, and that's it. So, say that you have homophones, you have right and right, then you add two new disambiguation symbols, which we are going to denote here as #1 and #2. And now these become distinct pronunciations, right? And that's it. Now your resulting machine will be determinizable. Similarly, if you have a word like book, whose pronunciation is a prefix of the pronunciation of another word like books, then you add a disambiguation symbol so that now it is, as the name suggests, disambiguated. Okay, the pronunciation is explicitly disambiguated. So now you've added all these additional disambiguation symbols. So what's the maximum number of disambiguation symbols that you'll need to add? It'll be equivalent to the maximum, the degree of homophony, which is prevalent in your particular setup, right? So once you introduce these new symbols, so remember that now you'll need some way of dealing with. So consider this to be almost a new monophone that you are introducing, right? So the context transducer also now needs to deal with these monophones appropriately, and so you need to kind of propagate these new auxiliary symbols that you have introduced in L all the way back through the previous two machines, which is C and H. So you do this just by adding self loops on the states in these machines, and they just take these auxiliary symbols as output and then produce the same auxiliary symbols as take these auxiliary symbols as input and produce the same auxiliary symbols as output, and they're just self loops. Okay, so you're just kind of helping propagate this all the way back to H, and once you reach the input side of H, right, there is no speech corresponding to these auxiliary symbols. These are just bookkeeping symbols, right? So what would you do eventually with the equivalent symbols for these disambiguation symbols which appear on the input side of H? Finally, once you have constructed the full decoding graph, any such disambiguation symbols which appear on the input side of D, you'll just replace them by epsilon, meaning there is no acoustic equivalent, but you can just replace them by epsilon because they can be, those transitions can be traversed, and the resulting auxiliary symbols can be produced without consuming any input symbol. Okay, so this again you will see in your Kaldi ASR system that you will build for assignment 1, that you will have an L.FST and you will also have an L_disambig.fst. Okay, and that is the resulting FST after you have included these disambiguation symbols, so that L disambig composed with G is a determinizable machine. Okay. All right, so that is about constructing this decoding graph. Now let's move to the crux of how to search through this particular D. So I'm given a test utterance O. How do I decode it, right? How do I identify what is the most likely word sequence from this particular machine D? Now let me go through a series of steps. So if I'm given a test utterance O, so let's assume this is some O1 to O capital T, okay, where each OI is your acoustic feature vector, right? Now, let me assume I'm going to construct an FST X, which looks something like this. Okay, so this is a sausage-like structure, right? So from each state, I have these transitions. So this is an acceptor. Okay, this is not an FST. This is an acceptor. So you can see that the only symbols on the transitions are these acoustic indices. And recall, these acoustic indices map to distinct triphone HMM states, right? So each F0, F5, F500 will map to specific, second, third state within a particular triphone HMM. Okay, and now what are these accompanying weights? The accompanying weights actually correspond to your emission probabilities, your observation probabilities. And recall, we are always working with FSTs in the tropical semi-ring. So all the weights on all my transitions are negative log probabilities. Okay, they're not probabilities. So here specifically, if I'm consider now, let me break this down a little further. Each of these transitions correspond to a time step. So this will correspond to O1. Okay, this will correspond to O2, and finally this particular last link in this sausage like FST will correspond to O capital T. Okay, and now within each of these sausage links, you have all these transitions, right? One transition corresponding to each triphone HMM state, and the corresponding probability will be the emission probability. So this is the probability that I'm seeing OT given that I am in state J, right? This is my emission probability. So remember this notation from when we discussed HMMs and observation probabilities. So this is the probability of emitting O small t given that I'm in state J. And how do I know what state J is? Because F sub J, I know exactly maps to a particular state, an HMM state. So I just need to look up what was the emission probability um, of generating this OT, the OT at this particular time step T, given that I was in state J. And that is what each of these scores mean. So now you can see X, this X that I have constructed encodes all the possible emission probabilities, okay, for a particular test utterance O1 to O capital T. Okay, so the first thing that should kind of cross your mind is this is a very, very large machine. Okay, even though its topology is very straightforward, it's just this sausage-like FSA. I have so many transitions, right, within each link, and the length, because capital T is fairly large, it can be of the order of 200 to 300, 400. So I have this large kind of linear chain with the sausage links, and each of these sausage links in itself has many of these transitions, right? As many transitions as I have triphone HMM states. So this is a huge machine, but nevertheless, that's why I say let's assume ample compute. Let's not worry about how long this is going to take to build and then further compose. Let's assume we construct this X. If I have such an X, then my decoding problem reduces to the following, which is compose X with my decoding graph D, okay, and find the W such that it has the lowest weight in this composed machine. And why lowest weight? Because I'm dealing with negative log probabilities, right? So the lowest, the shortest path in this composed machine will correspond to the most likely word sequence. So here, this notation, here pi corresponds to path in the composed FST. Out of pi is the output label sequence of pi, right? And that is the W, the word sequence that I eventually care about, the final word sequence corresponding to my input, which is used to implement X, the machine X, construct the machine X. So this is my resulting decoding problem, which completely now has been implemented using WFSTs. But now moving to kind of computational considerations. So X is really large, okay, and X composed with D would just be completely infeasible computationally, because D itself is very large, especially for large vocabulary systems, and then X is also very large. So it's never typically done like this. And this is one way, is an easy way to understand how you can implement the ASR decoding problem using WFSTs, but it's never explicitly done this way. D is actually traversed dynamically using search algorithms like beam search and so on. Okay, so this we will discuss in much more detail when we talk about search algorithms. So for now, you can just think of this as being kind of the WFST implementation of an ASR system, and the exact specifics of how this is done in computationally efficient ways using approximate search algorithms we will cover in much more detail later. Okay, so that's the entire decoding pipeline. Here's just one slide to kind of drive home the impact of using these WFST optimizations. Okay, so here you can see if you start with L compose G, with this, which is not determinized, you determinize it. Okay, this is the resulting machine. So one here, something to note here, Determinization doesn't really make the machine smaller, right? That's the job of the minimization algorithm. Determinization's job is actually to make sure that there is a unique path for a given input sequence. And so the machine could even become bigger than the original machine. It's just that search becomes much more efficient through a determinized machine. So here is kind of the what is known as real-time factor. So real-time factor meaning given a particular speech utterance of n seconds, how long does it take to decode that particular utterance? So if you have a real-time factor of 1, what that means is that for a 5-second utterance, you should not take more than 5 seconds to decode it. Okay? And you can see that with the determinization, your real-time factor becomes 1. Okay, it becomes really, really quick, as opposed to when you didn't have any determinization or optimization. This is just completely unacceptable, some 12.5. But kind of enforcing this entire pipeline, HCLG, and then determinizing it and so on has a significant impact on the real-time factor. Okay, this is just one slide to kind of say that optimizations are useful. All right, so that's the complete pipeline, the HCLG pipeline, which you'll also encounter in your Kaldi assignment. Now, in the next module, we are going to look at the GFST. So here, the GFST that I showed you, the example I showed you was like a toy example, right? This is nowhere close to kind of legitimate language models that we would like to build. So let's look at n-gram models. We'll also explicitly look at how n-gram models are represented as finite state acceptors. So that's coming in the next module.